found that electricity dominated. What I'd like to start doing today is a very nuts and boltsy thing. Basically, I'm going to do a review of force addition. This is a skill that you should remember from Physics 1. So this is basically, I'm just going to do a quick review and show you kind of like how you might incorporate Coulomb's law into that. But the answer is really not that much. You just use it to plug in the sizes of forces. But other than that, you're still doing your same components, SOHCAHTOA, all that stuff. So let's just do one of those. I'm going to jump straight to 2 dimensions, just to save stuff later in the course. So this is where you might need some SOHCAHTOA. 1 dimension is easier. You just pick one direction to be positive. Things that point that way are positive. Things that point the other way are negative. So let's do an example. I'm going to put 4 charges on a square. I just happen to pick a square, because why not? Let me give you the amounts of those charges. I can find this. Okay, so Q1 is plus 10 microcoulombs. Q2 plus 5 microcoulombs plus 6 and minus 3. Okay, it's going to be, the whole thing is a square of side L, which is 3 centimeters. So that's the setup. Let's just, it's a particular configuration of charge. We just want to be able to analyze it. First thing, part A, I want to draw all the forces acting on Q2. So why Q2? Well, I'm just going to pick one that, for some reason, is our charge of interest. And then, once I've done that, the natural follow-up question is, what is the net force on charge 2? So, first of all, in order to assist my drawing in part A, so that I don't have to keep referring back to the list, I'm going to label the charges as plus, 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 and minus here, so that I can figure out who attracts and who repels who without having to refer back to my list. Always better to get information into the diagram. And the forces that act on Q, they're going to be a grand total of 3 because there are 3 charges in the vicinity. How are Q1 and Q2? How are they going to exert forces on each other? They repel. So that looks like this. And for labeling purposes, remember from Physics 1, not that we did it a ton, but in Physics 1, we discussed Newton's third law. And Newton's third law means that these forces are equal and opposite. The nomenclature is that this is the force on charge 1 from charge 2. So the first number is what it's acting on, and the second number is where it comes from. Likewise, this is the force on charge 2 from charge 1. So sometimes you might want to drop that second subscript. You just want to be concerned about what the force is on and not necessarily where it comes from. It's just the environment. Usually in Physics 1, it's just the environment. But here I do want to specify where it does come from because I want to make sure that everything is accounted for. So that's the mutual repulsion of those 2. How about these 2? What happens with these 2? They attract. Newton's third law says that that is a mutual attraction. Those forces are same size, opposite in direction. What would be the subscript for this force right here? 2, 4. It's on 2 from 4, and here, of course, 4, 2. And then finally, we have, we can't forget about Q2 and Q3. Remember, you have to account for all of the charges. Okay? You can't just take the nearest ones. Their barriers cannot block the force. You have to account for all forces. These are going to repel as well. And of course, in directly repelling, that puts a force on a diagonal, which is might be inconvenient to you, but nature doesn't care. So this is force 2, 3, and force 3, 2. Now I could go on and on like this until eventually there were 3 arrows, 3 forces attached to each charge. Of course, 3 forces act on each charge because each charge has 3 neighbors. But I'm going to stop there because I do have all 3 already on Q2, which for some reason is my charge of interest. So I'm going to stop there. And then the net force on charge 2 will, of course, be the vector sum of these 3. F21, F23, and F24. So this subscript system is nice bookkeeping because then you can look at the equation and you can see that it's all good. We want the net force on 2, so 2 should be the first number here, 2, 2, 2. Those are the 3 forces that act on that charge. And then the other numbers in the list should be all the other charges. 1 and 3 and 4 act on it. Of course, you should never have F22. That does not make sense. You can't have a force on charge 2 from charge 2. Okay, that would be violating Newton's third law. Okay, that's like being able to pick myself up and carry myself out of the room. Okay, so no self forces. Forces come from other things. So as far as how to execute on this, let me remind you that basically we need to split this up into components, or we need to certainly consider their directions. How do you choose axes? You choose axes like this. Again, this is straight from the force problem solving strategy of physics 1. If you know the direction of the acceleration, pick one of the axes like that. So if you know the accelerations of particular directions, pick, say, your x-axis, point that way. Classic example, inclined plane. That makes your life easier. If you don't know the direction of the acceleration, or there is no acceleration, then you can't do that. So instead, just try to make your life as easy as possible by minimizing your SOHCAHTOA business. So here, I'm going to choose this, not because I'm not open to other choices, but because then 2 out of the 3 forces lie along those axes, and only one of them is going to need further breakdown. So in my case, in the x direction, F net 2x component, I will have force 2-1, which is entirely in the plus direction. And I will have, I guess I can draw it over here, F23 can be split up into 2 components, plus F23 cos theta, plus F23 sine theta. So remember to assign plus and minus, remember to assign sines and cosines as appropriate. In this case, we have 2 different things that are contributing in the positive direction. So note, here's the direction, plus, here's the direction, plus. That's already taken care of. Everything that follows that should be a magnitude. And that is exactly why we have absolute value signs over here. Because we want to just be able to plug in the size of the force without extra minus signs somehow mucking up what we've already decided. We decided both of these forces to the right. And by the way, since both contributions are positive, there's no question that the overall net force is going to be to the right. To the extent that any of these forces acts in this horizontal direction, they all act to the right and none of them act to the left. So there's no question what's going to happen. And then, before we go too much further, I'm going to skip a line and do the y direction. The y direction, there is F24, which is entirely in the negative y direction, and then I have a component which is in the plus y direction. So I have, again, 2 components in the quote-unquote vertical or y direction. But now, we have, it could be plus, 0, or minus. Now, oftentimes you can actually get a sense of what the winner might be conceptually. So this is always good to have that conceptual thing to lie on top of this, so you don't necessarily have to depend on your calculator work going perfectly. So I'm going to see if I have a chance at figuring that out. So I have two things that are influencing this thing in the y direction. I have this force right here, and I have this force right here. So basically, we can take charge 1 out of consideration. There's no vertical aspect whatsoever. But Q4 will pull this thing downward, and Q3, by repelling it, has a portion of the force that goes upward. So let's take a look at advantages and disadvantages both of them have for the ultimate fate of Q2 in the y direction. So if a charge is going to be generally more dominant, does that mean it has more charge or less charge? So if you increase, so if you want the force to be bigger, do you want the charge to be bigger or smaller? Bigger, right? So if all things else were equal, which there aren't, by the way, but if all things else were equal, then we would look to see which of these two had more charge, because that means it's going to have a stronger interaction with the Q2. So we look at the list, we see Q3 and Q4, and we actually see that Q3 has more charge. So this Q3 exceeds Q4. So that's an advantage there. So that tips it as well. Maybe the plus y direction is going to win. Okay? So that's one advantage that Q3 has, but Q3 also has a big disadvantage. What's the disadvantage? What's that? What's that? It's at an angle, and there's another one. It's further away, exactly. So this one has the advantage that it's closer, and it is the entire force is devoted toward the y direction instead of just a component of it. Now, if all three of those advantages went to one of the charges, you know what's going to happen. Okay? If all of the advantages go to one charge, then you don't have to crunch the numbers to know which one's going to win. Now, in this case, we have that the advantages are, of course, mixed amongst the two, so we're going to have to just go to the numbers and figure it out. Okay? But you'd be surprised at how often, just thinking about advantage and disadvantages, if it's all stacked to one thing, you know the answer before you ever crunch it out. Okay? So, there are a couple homework problems where this will be important, okay? This kind of conceptual comparison. All right, so let's go ahead, and all we're going to do now is use Coulomb's law to fill in the magnitude of the force. And here's another advantage of the subscript notation. It tells us right away what two charges are involved, so we don't have to look back at the diagram. The force 2-1 will be charge 2, charge 1, and the distance between them. Now, when you're plugging in, let me remind you that the SI unit is coulombs. So don't plug in microcoulombs by mistake. Also, R has to be in meters. So what would be the distance between charges 2 and 1? What's this distance? 0.03 meters, right? So we get that 3 centimeters into meters. Remember to plug in SI units because that K constant is in SI units. So on and so forth. This one would be the K Q2 Q3 R23 squared. Again, make sure you put in the charges in coulombs, not microcoulombs. And here you'd have to be a little careful because, as we already noted, this charge is further away. So this distance is not 3 centimeters. It's what? Square root 8. Is that 3 root 2? I don't think of it that way. 3 root 2? Yeah, square root 18. It's a 45, 45, 90 triangle, right? So whatever the legs of the hypotenuse, or the legs of the two triangles, the hypotenuse is that times √2. Yes? Okay. I know it's 45 degrees because it's a square, right? Which, by the way, means that this angle is 45 degrees. So when I say theta here, I mean 45. The one angle where you can mess up your SOHCAHTOA and still be right, because cosine and sine are still the same value. By the way, let's say it was a rectangle. What would we do? This angle wouldn't be 45 anymore. This would not be √2 times the legs. But it's just a little bit of geometry, right? Let's say I gave you that this side was L1 and this was L2. How would you figure out the angle from those? Inverse tangent. How would you figure out the diagonal? If I knew the two legs. Pythagorean theorem. Yeah. So there's sometimes just some basic geometry involved here in figuring out the things you need. And one of the things you need for Coulomb's law is the distance between the charges. And however you can get that, you get that. So on and so forth. Let me tell you what comes out. Crunch it with your calculator. You should get something reasonably close, within reasonable round off to what I'm just about to give you. So the Fnet X comes out to be around 608 newtons. I have 608.2. And then this comes out to be minus 41.77, I guess. So it turned out that it was negative. So what that means is that as far as the y direction is concerned, Q4 is a more powerful influence on Q2 than the other competitor. But I should also remark that the y component is far smaller because, of course, in the y direction there's a competition, whereas in the x direction everybody's on the same page, right? So those are the two components of the net force, and then how do we reassemble them into an entire force? Is that? Good, right? But more specifically, like let's say we wanted to find the magnitude of the net force, we would use what? Pythagorean theorem. If we wanted to find the angle, inverse tangent, right? You get your one component, 608.2. You put it head to tail with your other component, minus 41.77. You'd use Pythagorean theorem. To get the hypotenuse, you'd use inverse tangent to get the angle. Let me just give you the results. Fnet 2 is about 610 newtons, 4 degrees clockwise from the plus x-axis. About 4 degrees. Mostly x direction force with a small residual y direction force due to the unequal competition in the y direction. So you notice this is mostly force addition review. We just throw in Coulomb's law when we want to find the magnitude of these forces, but this should all generally be review. And so if we wanted to, say, complete our diagram, putting ourselves a nice arrow to signify how this force, this charge will feel, it will get pushed in that direction. And it will accelerate in that direction, of course, according to Newton's second law, F net equals ma. So I guess let me give you a little bit of a preview. This is getting a little ahead of ourselves, but this is what we'll be doing on homework number 2. Let's say for the purposes of this problem, we nail down these 3 charges, Q1 and Q3, Q4, so we put a nail through them or something so we can hold them in place. And then we are perhaps interested in Q2 because that's the charge that maybe can fly off and do anything, okay? So what would happen is that while these 3 charges stayed in place, this would fly off like this. So it would go, here's the problem. Once it gets right there, the force is different because it's changed its orientation and distance to all of the charges, right? So the acceleration and force is generally is not constant throughout the trajectory. Now you have two options for what to do about this. The first of which is that you enlist a computer which is really good at doing mind-numbingly repetitive calculations very fast. So what you do is you let the charge move just a little bit, then you recalculate the force and acceleration, you apply that to whatever velocity you've accumulated already, you let it accelerate a little more, then you recompute the force and acceleration and let that apply to the previous velocity it's accumulated up to that, and that's the kind of thing computers are good for. Obviously not practical to do by hand, because every time you move even a little bit, the thing that guides how you're going to move next, your force and acceleration, is changing. Well, luckily we do have a method of handling this in physics where the acceleration is not constant at all. We used it a lot in Physics 1. I'll remind you of an example. We had like a roller coaster loop-de-loop. The acceleration and force are definitely not constant throughout this trajectory, and yet we could get somewhere anyway. What do we use for that? Energy. So energy method could care less if the acceleration is constant or not. So we will move on to examine charge trajectories in terms of the energy method when we really get serious about doing that. Of course, there was that one big downfall to that. What was the one thing you had to give up in order to do the energy method? What can you not find? What was that? Time, that's right. So we're going to have to give that up at some point, finding the time it takes for things to happen. But you will be able to say when the charge flies off, when it gets to its final destination, however we define that, we can get how fast it's going there. Okay? So that's a little bit of a preview about where we're going. We'll do that in homework number 2. But there are a couple orders of business we need to take care of first. And let me just tell you a little bit about what they are. First, we have to talk about the electric field. That's an alternative perspective on the situation that we've just described when charges are exerting force on each other. So it's a different model or way of looking at that. We could have introduced it in Physics 1 as well. So of course in Physics 1 we talked about the force of gravity, and later on we talked about the energy method, including gravity, right? I could have introduced in between the gravitational field, but I had to save some fun for Physics 2, so we'll talk about the idea of a field in general. It can be used for many forces: kinetic field, electric field, even gravitational field. We just didn't bother in Physics 1. So that's one thing we need to get out of the way. And the other thing we need to get out of the way before we get on to the energy method, so this is the rest of homework 1, besides what I've already talked about. And then we also need to talk about something called conductors and insulators. This is kind of splitting off materials into 2 different categories, and that'll be the start of homework 2. And then the back half of homework number 2 is going to be all about the energy method. So I figured I'd mention it now at the time because it kind of naturally flows right out of this example. But we're going to go back and switch gears and get some other stuff that we need to have in our toolkit. Okay, are there any questions before I start in on electric field? Okay, so let's discuss the electric field. So to motivate what this is all about, let me go ahead and put down 2 charges. I'm going to label one capital Q and one lowercase q. I'll explain why in a little bit. There's nothing different about the 2 charges, they're just charges, but it's a nice way of labeling them. So, just for the sake of argument, let's say that they are both positive charges, right? So 2 positive charges, they're going to repel. So that's all well and good, but here's what people had a real problem with. How do they know to repel? They're not attached or connected anyway. It might seem like, oh, well, it's right there. Well, maybe this distance is 1,000,000 miles. They still exert a force on each other. The Coulomb's law, it has an 1 over r squared dependence. But the force doesn't go to 0 then until r equals infinity. And 1,000,000 miles is not infinity. So there will still be some small amount of force, potentially, that they will know to exert on each other. It's that really bothered people. How do they know? How do they know to exert? How do they know about each other? There could be 1,000,000 miles apart. Maybe there's stars and galaxies in the way. They have no idea. They don't have a clean shot to see each other. But yet they still know. They still know to repel each other. So, in order to kind of get around this, we introduce a construct called electric field, which in many ways is even more strange, but it also has a practical side to it. So that's ultimately why we use it. So here's what we say instead. This charge right here, which I call capital Q, puts some kind of pervasive influence into the entire universe. Just puts out the call, has no idea